Wolfram and Schulich leaders logging in from Canada and Israel and other countries around the world. We hope 2021 is starting off on the right track and you and your loved ones are keeping healthy. Today, our program is truly privileged to learn from one of the greatest minds in computer science, physics, and business, Dr. Stephen Wolfram, the creator of Mathematica, Wolfram Alpha, and the Wolfram Language, originator of Wolfram Physics Project, founder and CEO of Wolfram Research, and the author of A New Kind of Science and other books. Thank you to Dr. Wolfram and your colleague, Danielle Rommel, who have been so generous to set up this exclusive session for our Canadian and Israeli Schulich Leader Scholarship recipients, the next generation of technology innovators. After Dr. Wolfram's presentation, we'll have 30 to 45 minutes to dedicate towards Q&A. And at that time, we'll review the main chat feed and we'll ask you to raise your hand to find an order. We would like to alternate between Canadian and Israeli Schulich leaders. And at that time, it would be great if you could actually unmute yourself and introduce yourself quickly, your name and perhaps city or university and program, and your question for Dr. Wolfram. And so we'll do that at around 1:15-ish. Anyways, without further ado, I'll pass the Zoom stage over to Dr. Stephen Wolfram for his presentation, Changing the World with Computation.
Great, thanks very much. Nice to meet you all. I hope I'm going to try and talk for as short a time as possible so we can have as long as possible for discussion. But I want to talk about this idea of computation that I kind of think is probably the most important idea, certainly in the past century, and one of the more important ideas in the whole sort of history of intellectual development. And I've been lucky enough to be involved in a bunch of aspects of sort of the development of this idea of computation. And we kind of, I think, still, even though a lot has happened, we're still in the kind of early stages of seeing the implications of this idea of computation. So maybe some of you have, hopefully many of you have seen. Actually, let me ask you, who here has used Wolfram Alpha? If you can, some people, okay. Let's see. Usually in this demographic, it's usually a large fraction. Okay, I see lots of hands. That's a good sign. Great. All right. So this is kind of probably the most consumerized piece of what we built in kind of using this idea of computation. And the notion is to make computational intelligence available to everyone and to kind of take the knowledge that exists in the world and make it as computable as possible. So that if there's a question that can in principle be answered from things our civilization knows, make it so that we can automatically get those questions answered. And people in your demographic will often use Wolfram Alpha for things like math and chemistry and so on, gets used for lots of other purposes in lots of other places and companies and so on. And maybe I can, one thing you might wonder is, how did this creature get to be created? Maybe I'll tell you a little bit of the personal backstory of what led to this. Then I'll talk a little bit about kind of the technology underpinnings. Then I'll talk about kind of the intellectual underpinnings of this and what that kind of means for the future. So how did a thing like this get created? Well, so it's kind of a long story. But when I was a kid, probably quite a lot younger than most of you guys, I got really interested in physics and I started reading books and learning about physics and so on. But there was one very frustrating feature of doing physics, which was that to do good physics, you had to do all kinds of mathematical calculations. And I found these mathematical calculations really boring. And I was like, this is very mechanical. It's not a good use of a human's time. That time, this was the early to mid 1970s. Computers were starting to be to the point where one could use them for things. And so I started realizing, yes, one could use computers to do this kind of boring math that I didn't want to do. And gradually, I kind of, that was sort of the early origin of building Wolfram Alpha, was that I didn't want to do this math myself. So I wanted to build computer systems that would do it for me. And many years later, that led to Wolfram Alpha. But And when I was doing physics in the late 1970s, I was lucky enough to be involved in particle physics and cosmology and things at a time when they were sort of in their golden age. I mean, one of the things one learns by looking at different fields is that there tend to be these sort of fields go through these cycles. There's some methodological advance, and then there's, and in the case of particle physics, that was the success of quantum field theory at that time. There's some methodological advance, and then there's kind of 5 or 10 years of kind of low-hanging fruit to be picked. And lots of exciting things happen, lots of people go into the field and so on. The field really advances, and then all the low-hanging fruit has been picked, and then you've got decades or more when the field is kind of fairly static, waiting for the next sort of methodological advance. I mean, we see that in modern times, you know, like machine learning is probably 2/3 of the way through its low-hanging fruit rapid expansion period. And it's always interesting as one looks at different fields to sort of figure out what are the ones which are at a particular moment in their kind of rapid expansion phase, because it's always fun, you know, the things I did when I was a teenager in particle physics, people still use today, not necessarily because they were that wonderful, but because I happened to be involved in a field that was sort of in rapid expansion, and that was the first time that these things could be done. And after the sort of rapid expansion phase, things went into kind of a cruise mode. Well, I think this idea of computation is the thing that is driving lots of kinds of rapid expansion in lots of fields. And the full idea of computation is bigger than most, and it's more like a 50, 100-year story of kind of things that are made possible by that methodology. But in terms of well, let me perhaps show you. So one question is, how does Wolfram Alpha actually work? What is it doing? I mean, it's taking some natural language query. I don't know, what is the population of Canada? I wonder what the answer to this is, divided by Israel. And oops, why is this? And it will take that natural language question and give us an answer and make some plots that it thinks we'd find interesting and so on. What's actually going on here? There are several pieces. One is it's got to interpret that natural language. Then it's got to actually have the underlying data to be able to give us this answer, and it's got to have that in a form where it can compute the answer. But a key part of that story is, what does it turn this kind of natural language into? It turns it into a symbolic computational language. And this is the main thing that I've spent the last, 40 years or so working on, is sort of trying to build that computational language to be able to represent questions about the world and things that one can compute. So maybe I can show you a little bit of that, just for the sake of getting some concrete idea of what's going on, and then we'll talk about some of the sort of principles that lie behind this. But so let's see. So this is what we now call Wolfram language. It's the same technology as Mathematica, which first came out in 1988. But so kind of the idea is be able to compute about sort of anything, and sort of the bigger picture. Well, let's just do a little computation. Let's say we have a random graph here that might represent some piece of some social network or some such other thing. We could say make a community graph plot of that. Take that, do that computation. Maybe we could say take let's get an image of something. How about picture? Oops. See, every time Zoom somebody shows up in the Zoom, it steals my cursor and it doesn't let me type. So okay. So let's say picture of an eagle or something. So what this is now doing is taking that. Oh, fascinating. Okay. Decided that the let's see, this is, oh, that's interesting. It's a very bizarre interpretation. Okay, let's try picture of an ostrich. That's the life of natural language as opposed to kind of computational language. Once this is translated into computational language, it's clear what kind of what kind of a thing this means. So okay, so we have an image here. We can say let's go and do a computation on this image. Again, the concept is, if there's something that we can compute with, like an image, let us be able to do that. And for example, another kind of thing is, let's say, is being able to deal with kind of things in the real world. So for example, let's say we get a list of words, let's say words in English. We could, for example, we could now say, take the first letter of each of these words, see what we get. Or we could say, make a word cloud of the first letter of each of these words in a dictionary in English, and then we get the result. Or we could do the same thing. We could say, do that for some other language. Let's say, I don't know, French, let's say, and now we'll give the same result for that, hopefully. There we go. Okay, so this is kind of telling us which parts of a dictionary will be biggest in French, for example. But so the concept here is be able to take sort of things in the world and make and represent them in a computational way. So for example, if we say something like, well, let's try, how about, let's see what happens if I do this. I wonder whether this will work. See whether this can be understood in natural language. Okay, there we go. Okay, so that translated that natural language into some symbolic form, and this will tell us, so let's say, let's get an entity list here. This says, it asks what are the 10 largest cities in Canada. And for example, I could now say, let's, for example, say, make a geographic plot of those. Or let's say you want to go visit all those cities. So let's say we take those cities and we say, let's call that cities. And we could say something like, find shortest tour of those cities. So this is saying, find a trip around, find a way to visit those cities where the total distance is minimum. So let's see if we go like this. And then we say something like, geo list plot of this, and then we say joined is true. That should show us some how we can do a kind of tour around the 10 largest cities in Canada. And the thing that I always find interesting about this is, what makes this possible? What makes this possible is that we've spent many decades now kind of curating data about the world to get it to the point where we can actually compute about things we can actually kind of know enough about the world to be able to do these kinds of computations. And you can deal with all sorts of different areas. I don't know, we could say something like, let's take I don't know, let's take movies, for example. Let's say we'll take let's say we want 10 random movies, and these all kinds of scary things may come up here, but let's say we could say let's get see how many of these we have. Okay, most of these we're missing. Let's try again. Let's see how many of these. Okay, so a bunch of these movies we have the movie posters. We could say, for example, let's say let's just get rid of the ones that we're missing here, and then let's go ahead and say, for example, let's find out what colors were most common in the sort of in the RGB color space, or this is XYZ color space. What colors were most common in those movie posters? And we probably then go and correlate some of the more horrifying movies there with the ones that had red covers and things like this. So in any case, this is kind of the concept is to be able to represent things in the world computationally, and to be able to find kind of a way to if it's possible to compute about something, be able to do the computation. Well, so one question is sort of what's the intellectual underpinning of all of this? And I think one of the things to realize is that sort of a question of, if you want to represent the world, what's the best way to do that? And in kind of, in science, sort of an idea that was something that sort of originated maybe 300 years ago or so now, was if you want to represent things in the world, write down a mathematical equation that represents them. That was kind of the big idea of people like Galileo and Newton and so on, of representing the world in mathematical terms. Well, many years ago now, I kind of got curious whether there were ways to sort of generalize that approach to thinking about the world. But what that approach at an underlying level does is to say, let's see if there's sort of a formal way to represent the world in terms of some underlying rules and so on. So the question is, are those underlying rules that come from sort of mathematics, or can they be something more general? And so I realized, this was in the early 80s, that there was kind of a more general way to approach things, to say, to think about sort of arbitrary rules that govern the behavior of systems. How could we represent those arbitrary rules? Well, the paradigm that we now have for doing that is computation and programs and so on. And so that got me interested in the question of, okay, if we're going to represent the world in terms of programs, what might those programs be like? And that got into sort of a basic science question of, okay, if we just were picking, let's say, very simple programs at random, what would those programs typically do? And one might have thought that a question sort of as basic as that would have been asked and answered a really long time ago, but for all kinds of reasons, that question had never really been asked, and people didn't really have, and I didn't have, in fact, the right intuition about what the answer to that question might be. But it was pretty easy at the time to start just doing computer experiments and finding out what the answer to the question was. And let me kind of show you what I looked at. So the sort of simplest programs I could think of were these things called cellular automata, which in which there's just a line of cells. Each one is either black or white. And then there's a rule that just says at every step, decide what the center color of the cell will be based on the colors of its two neighbors on the step before. And so if we take a rule like that, we can just say, let's just take that rule and start it off from just one black cell at the top and say, what does it do? And we can just ask the computer, and there's the result. So we have this very simple rule that just says, basically, if you read through this rule, it's just saying whenever there's a black cell next to any cell, make the cell black on the next step. And applying that rule just 40 times here, we get this pattern here. Well, we can say, let's change that rule a bit. Let's say we have this rule here. Let's see what that rule does. Okay, again, oops, keeps on stealing my mouse. There we go. Okay, with this rule, again, very simple rule, and it does kind of what one might expect, which is very simple rule, very simple behavior. Question is, if you try different rules, is this always what you'll see? So let's say we try this rule here, try that, run it here. Okay, it does something slightly more complicated. If we run that for a while longer, we will see that it makes a pretty intricate pattern. But nevertheless, it's a pattern that, although intricate, has a great deal of regularity to it. And so we might conclude, as I at first did, that if the rule we're using is simple enough, the things we get out must at least have a great deal of regularity. But then, long time ago, I tried doing sort of the obvious computer experiments, kind of like once you have a sort of computational telescope, you can kind of turn it to the sky and see what's out there in the computational universe. And that's what I did. And this is what you find. So this is just looking at the first 63 possible rules. So we're just changing the pattern of bits here. This is looking at the first 64 possible rules of this type. And many of them do just very simple things. You start off with one black cell and you just get black cells, a single black cell forever, or you get these stripe patterns, or you get these nested patterns. But then looking out with this sort of computational telescope, you find this really surprising thing. This is rule 30 in the numbering of these particular rules, and it's sort of my all-time favorite science discovery. So let's take a look at what goes on there. So this is rule 30. It's just one of these rules that says for every configuration of cells what will happen next. But let's try running it for a while. This is what happens. So you might have thought simple rule, simple initial condition, everything that happens must be very simple, but it isn't. Instead, sort of out in the sort of computational universe of possible programs, the thing that we end up finding that we don't get simple behavior. We get instead this very complicated behavior. There's a certain amount of regularity over on the left, but if you, for example, look at the center column of cells here, for all practical purposes, they seem completely random. So this is a really bizarre thing, that sort of in this computational universe of possible programs, even very simple programs can produce very complicated behavior. So what? Well, the thing that I was most excited about is one of the things that's most surprising about a lot of the natural world is how complicated the things one sees in it are. And so there was this sort of question, what is the secret that nature is using to make all this complexity that it makes? And what I realized is that what we're seeing in the computational universe is kind of a sign of the secret that nature is using. Nature is basically picking the analog of these computational rules, and it's very easy from these computational rules to make very complex things. Now, when we do engineering, for example, we have tended to avoid these kinds of situations. We've tended to always want to set up our engineering in such a way that we can readily foresee, what that system we're building is going to do. So we don't want something like this, where you start off with some simple rule and you get very complicated behavior. Now, we've been, in a sense, we should be aware of the fact that things like this happen. I mean, for example, when we write programs, the fact that there are often bugs in programs is a sign of a phenomenon much like this, that even though you've set up some rules, you can't necessarily foresee what their consequences will be. But there are all kinds of things that result from this sort of observation that even very simple rules in the computational universe can show very complicated behavior. I might say that well, one of the things that at first I did was kind of explore empirically, explore this computational universe and find all the weird creatures that exist there. And then the question is, what general principles can you deduce from this? And the most important general principle that I deduced is this thing I call the principle of computational equivalence, which is a very general principle that has many, many consequences, actually, not only for science and technology, but also for lots of other kinds of things. So what is this principle? Well, the thing to start off thinking about is, how do we think about the process of what's going on in this picture? We can think about the thing that's happening as being a computation. One starts off with some initial state here, and then one is just applying this computational rule over and over again, and the result of what's happening is some kind of computation. So the question is, how sophisticated is this computation? How does this computation compare to, for example, other computations we might do? Well, one of the things that one might have thought is, as you make the rules for a system more complicated, the computations that system will be capable of doing will get progressively more complicated. The big surprise, as far as I'm concerned, was that that isn't true. That above some very low threshold of these rules, the things one gets are sort of computations of as much sophistication as anything can muster. So that means that there's kind of, if one thinks about all these different kinds of systems, all these different kinds of rules, as soon as the behavior is not sort of obviously trivial, it turns out to be a computation of sort of maximal sophistication. Well, what does this mean, and how do we fit this in with things we already know? Well, one of the sort of biggest results of the whole kind of world of computation is something that was first kind of started to be realized in the 1930s, which is this idea of universal computation. I mean, if one goes back before the 1930s and one imagines how would one compute things, how would one do, additions, how would one do multiplications, things like that. For pretty much each different kind of computation one might imagine doing, one would think one has to get a new and different machine to do that computation. But the big thing that came about first with things like Gödel's theorem and then Turing machines and so on, was this realization that no, it's possible to make a single universal machine, which with appropriate programming, with appropriate initial conditions set up for the machine, will do any computation we want. that idea, the idea that it's possible to have universal computation, that one can have a sort of fixed piece of hardware that can be programmed to do lots of different things, that idea, which as I say, began to originate in the 1930s, was kind of is the thing that has led to kind of the possibility of software and basically kind of the whole computer revolution and so on. This principle of computational equivalence is a more extreme version of the same observation. It's basically saying that not only is it possible to make a universal computer, it's actually really easy to do that. If you just look at this computational universe of possible programs, it's pretty much any program that does not show obviously simple behavior will turn out to be as sophisticated as any other program can be and can, for example, achieve universal computation. So this, there's all sorts of consequences of this realization. It means that, for example, all sorts of systems in nature we can expect to be capable of sophisticated computation. It means that all these different kinds of abstract systems we study will also be doing sophisticated computation. Here's another consequence. So if we want to predict what's going to happen in this system, one thing we can do is just sort of run it and see what happens after however many steps, and just say, okay, after 1 million steps, there's a black cell in the middle, for example. But the question we might ask is, can we kind of jump ahead and predict what's going to happen? A sort of typical thing that one thinks about in science is, that to use science to predict what's going to happen in a system. Well, but this principle of computational equivalence says there's actually a bit of a problem with that, because in a sense, to make a prediction, we as the kind of predictors have to be in some sense computationally smarter than this system. What for this system takes lots of steps of computation, for us should be something that we can kind of jump ahead and work out the answer to. But this principle of computational equivalence says that that's not possible. In a sense, all of these systems, including things like our brains and so on, are computationally equivalent to what's happening in this system with this very simple rule. So that implies a phenomenon I call computational irreducibility, the idea that just because you know the rules for something does not necessarily mean that you can readily predict what the behavior of the system will be. Instead, it may be necessary to basically just follow through each step of the system to work out what it will do. And that's something that is sort of very surprising in terms of what one expects from science. It's kind of ever since people have been relying on science to just be able to work things out. Once we can make something scientific, we can work out the answer. That's something that's certainly been very evident in people's sort of beliefs about the pandemic and things like this. But what one realizes from this phenomenon of computational irreducibility is that that's simply not true. That from within science, so to speak, there's something which is showing that there's a limitation to what it's possible to do, what it's possible to kind of predict with science. So, and there are all sorts of consequences of this that sort of go beyond the merely scientific. Like if one's interested in questions like determinism versus free will and so on, this has many things to say about that. I mean, it's kind of, in a sense, it might seem to be kind of a downer that there's this computational irreducibility that stops one being able to make sort of fast predictions about what's going to happen. But in some sense, it's sort of good news, because if kind of everything that happened in our lives was something where you could just jump ahead and say immediately, the answer is 42 or something, that would be a kind of disappointing. This phenomenon of computational irreducibility kind of implies that the actual passage of time and the things that happen are doing something irreducible, so to speak. So anyway, the sort of exploring the computational universe of possible programs is something which kind of shows us that there's lots of richness out there. There's this kind of whole ocean of computational capability that exists there. And so one question is, what can we use this for? So first thing we can use it for is making models of things in the natural world. And one of the things that's been fairly dramatic is for about 300 years, when people were making models of things in the world, they would turn to mathematical equations to do that. In the last probably 20 years, there's been sort of a transition to new models of things getting made, not with equations, but much more often with programs. So by exploring the computational universe, we're kind of getting the raw material to make models of lots of kinds of things in the world. that's one thing. Another thing is we can imagine using kind of the things that exist in the computational universe to make to sort of mine them for technology. I mean, we have to think about sort of what is technology in general. Technology is kind of taking things that exist in the world and somehow applying them for human purposes. You know, we find magnets, magnetic materials, we realize we can use them to make compasses or whatever. We find liquid crystals, we realize we can use them to make now rather old-fashioned displays and so on. These are, it's kind of, we're used to kind of mining the physical universe for things that we can use for technology. But there's also now this whole computational universe that we can mine for technological purposes. And so, for example, even this Rule 30 cellular automaton, we've kind of made use of this as a generator of pseudo-random numbers, and you can also use it as a cryptography system. But it's just something you find in the computational universe, and then you realize you can entrain it and use it for technological purposes. So one of the general questions is sort of how do we take these things that exist in the computational universe and apply them to technology, make use of them ourselves. And so in a sense, what we have to do is there's a set of things that, there's a big set of things that happen in this kind of computational universe. There's a set of things we humans are actually interested in doing, the things we actually want to turn into technology and so on. I mean, there's and there's much where we just say, well, this is something that's happening in the computational universe, and it's very complicated, and it's perhaps interesting to look at, but there's nothing we can actually use it for. So in a sense, one of the things we want to do is to make this kind of bridge between the computational universe of possibilities and the things that we humans actually care about doing. And so in a sense, a large part of what I've spent much of my life doing is trying to make that bridge. And the primary bridge is this idea of computational language, the idea of having a language that can represent what we humans want to think about and do so computationally so that we can make use of the things that exist in the computational universe to do the things we want to do. And so it's kind of this thing where there's much that's possible in the computational universe. There's a certain set of things that we are interested in. Can we encapsulate those things in a computational language so that we can make use of what exists in the computational universe? And at any given time, we're making use of a very tiny part of the computational universe. It's sort of interesting to see that over the course of time, we kind of understand more and more about what exists in the computational universe, and we're able to entrain more and more of it for our technological purposes. But you know, one of the things that I've kind of realized is that when we think about making this kind of computational language, and I kind of showed you a few examples of what's possible with the computational language that we've built, what we're doing there is we're sort of trying to capture the things that we humans want to think about in computational terms so that we can have a computer help us and mine things from the computational universe to achieve the things we want to achieve. And in some sense, the thing that I see our efforts to build this kind of computational language as doing is something similar to what happened about 400 years ago when mathematical notation was invented. I mean, if you go back more than 400 years, you'll find that when people were talking about mathematics, they had to talk about using words. I mean, and that was fairly inefficient and not very streamlined. Then about 400 years ago, things like plus signs and equals signs and so on got invented, and suddenly it became much more streamlined to talk about things mathematically. And that then led to the development of algebra and then calculus, and then basically the mathematical sciences. And so what I see as kind of the objective now is to build kind of a computational language which can provide sort of the notation for computational ideas in the same kind of way that mathematical notation provided a notation for mathematical ideas, to sort of enable computational X for all X. I mean, for pretty much any field from kind of archaeology to zoology, and it's always an interesting exercise to actually take a particular field and see how this works. There either is now a kind of computational X, or there will be, and it will typically be the direction of the field to go in this kind of computational way. So kind of one of the things that was achieved with mathematical notation is not only, well, in the case of mathematical notation, it was a kind of a way of representing mathematics for other humans. similarly, with our computational language, one of the objectives is to have a language which allows just us humans to think more clearly about things in computational terms. But there's the amazing extra advantage that we can take that computational language and we can have a computer sort of work it out for us as well. So we get this kind of sort of superpower as a result of being able to interact with a computer in this way. Well, so there are lots of kinds of practical things that kind of computational language does. I mean, in our whole sort of technological setup, there are these notebooks that we invented, whatever it was, 34 years ago or something now, for kind of allowing one to create kind of computational essays where one sort of mixes kind of English or other natural language together with computational language as sort of a way to express oneself. And it's really a great way to kind of express ideas, because it lets one kind of leverage kind of this notion of computation to explain what's going on, and then lets one actually get the computer to do some large part of the work in generating the content of what one's trying to say. But so in any case, this is one of the kind of this whole idea of sort of making this bridge between what we want to do and the computational universe, kind of the idea of computational language. There's sort of many consequences of computational language and also these ideas like computational irreducibility. Let me mention one of them in kind of the world of kind of AI and the question of, okay, we're building a bunch of AIs. How should we tell them in general what we want them to do? How should we sort of define the AI ethics of the world? Well, one of the things to realize is, the thing we have to do is kind of define things like a statement like, okay, AIs, be nice to humans. How do we actually represent that thought? Well, what we realize is that we have kind of we're beginning to have a mechanism for doing that, which is computational language. We're beginning to get to the point where what would normally be something that might be a legal contract written in some natural language like English, we can actually turn that into something which can be written in computational language, because we have a computational language which can talk about things in the world. So we can actually write our sort of contract about what should happen in the world in computational language. And that's kind of how we can make this bridge between the things we want to say and the things that we can kind of implement for AIs. Now, needless to say, this notion of computational irreducibility puts a bit of a limit on what we can expect to have happen, because we realize from computational irreducibility that just because you define some rule for how things should work does not mean you can foresee all of its consequences. And so that's the thing where we realize that kind of, there isn't going to be this tiny little perfect AI constitution that just says in one line of code how we want the AIs to work. It's something where if we're to define what's got to happen, it's got to be sort of patched together in much the way that we find that human laws get patched together. Well, in any case, so lots of consequences of things like computational irreducibility and sort of this whole idea of computational language and so on. One of the things that one might ask is, okay, if we look at the universe, the physical universe and so on, how does this help us understand what's going on there? Well, for a long time, I kind of wondered, when one looks at physics, one of the things one sees is that as one sort of has tried to go to sort of to understand more about how fundamental physics works, things always seem to get more complicated. But once one's seen things like Rule 30, one might have a slightly different intuition. One might instead have the intuition, perhaps sort of underneath everything that exists in the universe, there might actually be some really quite simple rule. The question is, how might that actually work? And I started thinking about this back in the early 1990s in a fairly serious way, and took a long time to think through what might be possible. And then I kind of wasn't clear it was for all kinds of reasons. I ended up not pursuing this as much as I might. But the sort of question is, if we look sort of underneath physics, could there be some simple rule that's kind of running our whole universe? Well, I had thought about possibilities for how this might work back in the early 1990s, and I figured out a bunch of things that one could deduce from that. But it was only about a year and a half ago that I really got started again and made a bit of a breakthrough in understanding this, and ended up really trying to make a serious effort to see whether these kinds of ideas could allow one to understand what happens in fundamental physics. And to my great surprise and great excitement, it turned out that actually this worked really amazingly well. And so we now have realized that there's kind of a computational way to understand sort of fundamental physics, and in a sense to go underneath what's currently known in physics, and to see sort of in some sense what the fundamental machine code of the universe looks like. So in a sense, if we look at the progress of physics, the sort of the big things that happen in the 20th century, which have defined kind of physics as it has been so far, are general relativity, the theory of gravity, which came out in 1915, and quantum mechanics and quantum field theory, which originated in the 1920s, which is kind of the theory of very small things, so to speak. Well, what I kind of got to thinking is, if there is some simple rule that underlies kind of everything that exists in the universe, it must be the case that the things that we are used to, even notions like space and time, aren't things that exist within that rule itself. They have to be things that emerge from sort of the large scale operation of that rule. So one of the kind of assumptions that's been made kind of since Euclid, I guess, is that space is kind of a continuous thing, that you can pick a point anywhere in space. Well, one might have thought about materials like things like water, that it was a continuous thing as well, but we've known for the last 150 years that water is actually made of discrete molecules. Well, what I think now is true is that actually space is made of discrete things as well, kind of discrete atoms of space. And so then the question is, we have, let's say that space, like a fluid like water or something, is just made of these discrete points. How does space then work? Well, the thing we realize is that the minimal assumption is that space is made of lots of these discrete points, and the only thing we know is how these points are connected to each other. We don't know how far apart, in some sense of measurement of distance and so on, these points are. We just know how these points are connected to each other. And so what we do is to represent the structure of space as a giant graph. Actually, turns out it's more convenient to think about it as a hypergraph, where instead of just having two nodes associated with each edge, there can be any number of nodes associated with each edge. So in a sense, in our model of physics, all that exists in the universe is just this giant hypergraph with maybe 10 to the 400 nodes in it in our actual universe today. And and sort of everything that exists in the universe must be features of this hypergraph. So all of the electrons and quarks and particles and everything, they must all be features of this giant hypergraph. Well, the first thing to realize is, when you have a sufficiently large, even though the thing is at a small scale discrete, when it gets sufficiently large, it can behave, it can act like a continuous thing. Just like water, for example, we don't notice that it's made of discrete molecules. It seems like a continuous fluid to us. And actually, it turns out even the very derivation of kind of how the sort of continuous nature of water as a fluid works from its discrete underlying constituents, something very similar to that is possible to do for our models of physics. But it turns out that instead of getting the equations of fluid mechanics, the Navier-Stokes equations that you get in the case of fluids, instead the sort of continuum equations that you get for this giant hypergraph are actually exactly Einstein's equations that tell you the structure of space-time and that give you the phenomenon of gravity. So that's kind of an exciting thing. One thing to realize about these models is, we've kind of had the idea for the last 100 years that that sort of space and time is somehow very much the same kind of thing. In these models, that's not how things work. In these models, time is sort of the inexorable doing of computation, and space is just the extension of this hypergraph. So it's not obvious that things like relativity that kind of mix space and time together would emerge from this model. It turns out that when you think about sort of an observer who is themselves embedded inside this hypergraph, you realize that the only thing the observer is sort of sensitive to is a kind of causal graph of what the relationship between the different kinds of things that happen in the hypergraph are. And when you kind of untangle that idea, you discover that yes, in fact, you can expect that special relativity is true in these models. Well, one of the things that in the way this is set up, the basic sort of action of the universe is just whenever there's a piece of hypergraph that looks like one thing, rewrite it to a piece of hypergraph that looks like another thing. That's all that's happening, and that's what's kind of growing and modifying this giant hypergraph. Well, one of the things that one can ask is, what about quantum mechanics, for example? In sort of classical physics, kind of the idea is, you throw a ball and some definite thing happens. The ball goes in a definite trajectory. In quantum mechanics, sort of the main idea is that's not what happens. Instead, there's this whole kind of set of many possible paths that this ball could follow. And what we get to observe is some kind of probabilities that are determined by all these possible paths. So one of the things that's interesting in our models is that this phenomenon that there are many sort of possible paths that can occur is not something that you kind of have to add in by hand. It's something that's absolutely inevitable from the structure of the model, because it turns out that there are these possible rewritings that can happen in this hypergraph, but there are many possible different rewritings that can happen. There's nothing that tells you which one should happen when. But it turns out there's a phenomenon we call causal invariance, which is a thing that is closely related to a bunch of things that have been known in mathematical logic for a long time, that sort of guarantees that it doesn't, in some fundamental sense, matter in what order you do these rewritings. It's kind of like when you simplify an algebraic expression. You can do one piece of simplification first or another. It doesn't really matter. You'll always get the same answer. That's essentially the same thing as this computational, causal invariance property. And that causal invariance property turns out to be the thing that leads one to get special relativity, but it also it has consequences for sort of this this kind of set of all possible histories that occur. But the basic point is that in these models, it's sort of inevitable that you get this giant kind of branching structure of all possible possible histories for the universe, so to speak. And that phenomenon of this sort of branching and so on is basically the phenomenon of quantum mechanics. And it turns out then that just as you can kind of look at these kind of this hypergraph as representing the structure of space, there's something that you can do in this kind of multi-way graph of all possible histories. You can kind of take a slice across this multi-way graph and ask kind of what the relationship between different histories is. And that gives you something that is essentially a map of quantum entanglements. And that map is sort of exists in this thing we call branchial space, which is kind of a space of quantum states. That is kind of it's a different kind of thing from physical space. It's the space that comes about as a result of this kind of set of different possible branching histories of the universe. Well, so there's all kinds of things to say about this model, but one of the things that's kind of one of my favorites is one of the things one can do, as I mentioned, is to derive the Einstein equations, the equations of gravity, the equations that tell one if one is looking at a geodesic at a sort of shortest path in the universe, the path that a photon might follow in the universe. These equations tell you how the presence of energy, the presence of matter, will deform the structure of space and will deflect that geodesic path. And that's something one can derive in kind of the structure of space and space-time over here. When one looks at this multi-way graph and at branchial space, it turns out one can derive a similar result. One can derive also kind of an analog of the Einstein equations that operates not in physical space, but in this branchial space. And the extremely cool thing, as far as I'm concerned, is that the analog of the Einstein equations in physical space, when applied to branchial space, turns out to be exactly the Feynman path integral, which is sort of the core formulation of quantum mechanics. So in a sense, relativity, general relativity is the same theory as quantum mechanics, but general relativity operates in physical space, quantum mechanics operates in branchial space. And you can kind of see an interplay between these two things when you look at things like black holes and so on. But and you can kind of start to understand a lot of different phenomena by looking at that. One of the things that's been interesting about this theory of physics is that, in a sense, it is defining a very low-level machine code for the universe. And a lot of things that people have worked on, a lot of different areas of mathematical physics that people have been enthusiastic about, but which haven't really connected very well with what's actually observed in the universe. A lot of the kinds of mathematical structures that have been created there turn out to be things that directly apply to these models that we're studying. So in a sense, we're defining a low-level machine code, and a lot of these models, a lot of this mathematical physics that's been done can now be plugged in. It now has kind of a structure to plug itself into. Well, it turns out that the thing that's even more surprising to me than the fact that we're able to make such great progress with fundamental physics is that these ideas that emerge in these models of this kind of model of evolving hypergraphs and so on, those ideas turn out to be applicable to lots of other fields as well. So for example, distributed computing, the area where you have a lot of different computers and they're all sort of cooperating on a computation, but you don't know which computer is going to do a particular piece of the computation first. That turns out to be essentially the same problem as understanding the structure of space-time in these models. It's also basically the same problem as building a distributed version of blockchain where different kind of transactions can happen asynchronously from each other. But what's been really interesting and something I've been excited about last few months is kind of the interplay between sort of distributed computing and what we know in physics, and being able to take ideas from physics like black holes and event horizons and so on, and apply them to distributed computing, take ideas from distributed computing, apply them in physics. Actually, there's even another sort of connection, which is this kind of model of physics. The structure of it has a great deal of similarity to a kind of a bulk model of mathematics as well. So you might think of mathematics as something where you do a particular computation, but you can also think about sort of the bulk version of mathematics. What is the space of all possible theorems that you can prove given some particular set of axioms for mathematics? And that turns out to have the same structure as one of these multi-way graphs. It's like making these kinds of moves in our hypergraphs. You can just say this is the application of some axiom to some algebraic object that represents something in mathematics. And you build up this whole kind of multi-way graph type thing, which represents the sort of space of all possible mathematical theorems. And then when mathematicians, so to speak, get to are proving theorems, they're basically following a path in this essentially meta-mathematical space. And so far in the history of human mathematics, there are about 3 million theorems that have been published in the literature of mathematics. That represents a sort of a tiny piece of this kind of bulk space of all possible mathematics. And so you can start thinking about all kinds of questions about what is the infinite limit of mathematics. Questions like, why is it that mathematics is even possible at all? Why isn't it that most theorems that we try to prove end up being undecidable in the sense of Gödel's theorem? Why is it that mathematics, as humans explore it, ends up being just something that avoids those kinds of issues? And these things quickly sort of enmesh with ideas about computational language and ideas about sort of what we humans are interested in studying versus what exists out there in the sort of computational universe of possibilities. But in any case, it's been really exciting for me to see that kind of the ideas that were originally developed for our physics project end up being applicable in all these other places and end up providing kind of this sort of Rosetta Stone set of connections between different fields. Well, let's see, I've yacked on longer than I intended to, but I perhaps have given you some slight flavor for sort of this computational paradigm that I think is so important, that I've spent such a long time on. I mean, I could talk also about kind of how one actually gets to figure out and do things like this in the world, and that involves companies and trying to actually build products that are useful to people, and trying to kind of merge what is kind of intellectually, the sort of intellectual front lines with what's actually practical to do in the world, it's sometimes a little frustrating because one can realize that the things one does may end up being things that, I mean, it's kind of personally satisfying if one does something where one says, if I hadn't done this, this probably wouldn't have been done for 50 years or so. But sometimes there are things that one builds where one says, this is something which is clearly very useful, but it's going to be a long time before people really understand what they can do with it. And I think I sometimes think that a lot of my activities consist of sort of building artifacts from the future and doing my best to deliver them today, so to speak, and to have people understand what can be done with them. But one of the things for me personally is, as one builds kind of more of these sort of artifacts from the future, one gets to be able to use them oneself and see even further ahead. And I guess in my life, I've sort of alternated between doing basic science and doing practical technology development. And I've kind of done about 5 cycles of that alternation. And the thing that's been really, really interesting for me is that sort of I build a piece of technology that provides tools that allow me to take sort of next steps in basic science. And then sort of in essentially all cases, even though I hadn't really seen it coming at all, I'm able to use that basic science to realize that one can take another step on the technology side and sort of continue this cycle. All right, I mean, I should stop there, and I'm really happy to have discussion, questions, comments about any of these kinds of topics or anything else. So I see a few hands up. So let's see, I can't read.
Thank you, Dr. Wolfram. That was phenomenal. So we'll call on Atif to unmute, and he'll be the first question. Atif, if you could introduce yourself, and then we'll try and alternate between Canadian and Israeli Schulich Leader Scholars to ask questions. So
Great.
Please use the raise hand function if you want to get in the queue.
Can you hear me?
Yep.
Yes.
Awesome. Hi, nice to meet you, Dr. Wolfram. My name is Atif Mahmoud. I'm a third-year student studying software engineering and combinatorics and optimization as a double major at the University of Waterloo. Unfortunately, my video is not working, but hopefully my voice is elegant enough that you don't get bored.
Yes.
So thanks so much for your presentation. It was both technical, beautiful, and practical all at the same time. And it's hard to do, so I commend you for gripping my attention so well during that entire period. So an exciting idea to me is your principle of computational equivalence. Like, the first thing that came to my mind was the proof that there exists a 4-coloring for every planar map or graph. And what's exciting about this idea is that there are several fundamental truths about nature and mathematics that we can only really solve by exploring the complexities in their entirety. That's to say that the problem isn't reducible only to those relatively small axioms and theorems that we use to try and foresee or predict the solutions to other proofs in a similar field, like the 5-coloring, for example. And mathematicians typically tend to search for elegant proofs to their problems, and people today still search for a more traditional proof to the 4-coloring problem. So here's the question. Do you think it's reasonable to argue that there are plenty more of these situations in mathematics, nature, and physics that haven't been discovered or explored enough, simply because we haven't exhausted the tree of possibilities down what seems to be an unfruitful branch at first? And is computation the solution to this, with perhaps the new generation of mathematicians and computer scientists leveraging its power to unlock these kind of branches that we can't foresee down?
Right. So I mean, first point is, experimental mathematics is something that has not been explored nearly as much as it should have been. Many famous mathematicians of old, from Gauss to Ramanujan and so on, used to do mathematical experiments. They didn't tell you about that. They only told you about the theorems they proved. But they discovered what might be true, whether it's the prime number theorem or some exotic mathematical result of Ramanujan's, by doing experiments. And there is a methodology to doing computational experiments in mathematics that's really powerful, that some people know, but it's not as widely used as it should be. Now, one of the things that happens when you do computational experiments in mathematics is you start ending up with things you find are probably true, or things you wonder might be true, that are just sort of out there in the ocean of possible mathematical results. And the question is that something where you can reach it by a proof? Is that something where the actual, or is it something which is kind of part of the mathematics that cannot be reached by a finite length proof, for which the thing you find is basically undecidable? So first question is the mathematics that if we just pick mathematical propositions, at random, and we say, is it true, is it not true? How many of those will turn out to be decidable? How many of those will turn out just not to be connected to the things that we can reach by theorem proof type methods? My guess is, and my experience in sort of the computational universe is, the vast majority of things questions you pick at random will not be reachable by theorem proof methods. But so if we think about what is mathematics, mathematics is this sort of human activity that consists of kind of exploring further and further out in this kind of branching tree of things that we have managed to prove theorems about. I mean, one thing to realize is when we have a what does it mean to prove a theorem? What's the point of proving a theorem? I mean, let me show you an example here if I can. Let's pick up. Let's see, where should I go here? All right, let's just go to this. Where do I go here? Actually, go this. Let me show you something. Here we go. So here's a theorem. If we look at Boolean algebra, there's a question of what is the simplest axiom system that exists for Boolean algebra for basic logic. So I found about 20 years ago, I found this is the simplest possible axiom system for Boolean algebra. Okay, what's the proof of that? Well, this thing here, if I can, this thing here, if I can expand it, is the proof generated by automated theorem proving. It's a big long thing with 100 steps and so on. And in 20 years, basically nobody has understood this proof. We can show that it's correct, but nobody understands it. And so, you know, what's happening here? I mean, what's happening is that a common objective of proof is to have a way to be able to explain to people why something is true. To do that, you have to have kind of a narrative that you can tell about what's going on. But this is just sort of raw computation. This is kind of just like, it's a proof, it's true, but there's no narrative that explains it. And for example, in the proof of the four-color theorem, that's one of the issues, that there isn't a narrative that explains in steps what's true. It's instead just, here's an enumeration so you can see that it's true. So this question of when can you get a narrative to explain what's true? When do you just have to say, follow through the computation and see what's true? That's a very interesting issue. And for example, it comes up in machine learning right now. If you run some complicated neural net, you can, you use Wolfram language, you can look at the insides of the neural net, you can see all the steps it goes through, and then you say, what's really going on in this neural net? And the answer is, we can't really say. We don't have a good narrative that can describe what's happening inside that neural net. Might be the same as looking at brains. We can say, we look at all the neuron firings in our brain and we say, how do we explain what's going on in the brain? And what you realize is this actually comes right back to this kind of computational language type question, because what it really involves saying is, can we break down this kind of long sequence of computations into pieces that are sort of familiar enough to us that we might give them words and we might say we understand them? I mean, in a sense, the development of even a human language is all about sort of taking what exists in the world and breaking it down into kind of symbolic pieces where we can give names to different kinds of things, and then we can reason in terms of them. So one of the questions then is to what extent can things that exist in the computational world be broken down and into pieces that we can sort of turn into human narratives? And in mathematics, that's sort of a really interesting question, is to what extent we've got a certain narrative that has been developed in mathematics, certain areas of mathematics have been developed. To what extent are those all the areas that could be developed? Well, the answer is it's not even close. The answer is, I mean, I've looked at these questions about sort of what the space of possible mathematics is. And for example, one can look at, let's see, where's a good example of that? Let's see, here we go. There's kind of a picture of different possible areas of mathematics, different possible axiom systems of mathematics, different possible theorems of mathematics across the top. And this is sort of an ultimately desiccated form of mathematics, where here's the field of mathematics going across the page, and here's the theorems that are true in that field. And each one of these fields represents a different potential area of mathematics. And of all possible fields, only a tiny number have been explored, and there doesn't seem to be anything obviously special about them. In fact, the reason I looked for that simplest axiom system of Boolean algebra was trying to understand, of all possible theorems and axioms in mathematics, which ones are the ones that have been sort of most, which ones have we actually explored? Where do they live in the space of all possible mathematics? Actually, another thing I looked at just recently was the question of, if we just look at something like Euclid, Euclid was sort of the original kind of axiomatizer of mathematics. You know, he wrote down kind of 10 basic axioms of geometry, and then he proved 465 theorems. And so the question then is, what did that look like in the space of all possible theorems? And these are pictures someplace here. Well, this is basically a picture of the theorem dependencies in Euclid. So this is kind of showing us the tiny corner of metamathematical space, of the space of all possible theorems that Euclid chose to explore. And this whole question about what is there to explore, what parts of mathematics are sort of accessible to us humans, are there parts of kind of metamathematical space that are fundamentally inaccessible to humans? To what extent can we, what is the ultimate limit of mathematics as sort of the limit? We've got to 3 million theorems. What is the limit where we go to an infinite number of theorems? These are sort of all really interesting questions. And the thing that I think you're basically asking is, how much of mathematics, in some sense, mathematics is a story of taking what exists in metamathematical space and sort of figuring out human ways to talk about it. And we've got a certain distance in mathematics. We progressively build out in these certain directions. There's sort of a question of to what extent, how systematically can we build out in these different directions? What kinds of things count as being interesting for us in mathematics? Another thing I might mention, sort of a surprising thing again that I found long time ago, that's not the right thing, is this question of, if you take all possible theorems, which ones do we humans think are interesting? I mean, this is a general question. If you take all possible chemicals, all possible graph structures of chemicals, all possible, hydrocarbons or something, which ones are interesting enough that anybody will bother synthesizing them? These are all questions that are, it turns out for mathematical theorems, at least in one case, I was surprised to discover that there were actually some objective criteria that you could use to sort of decide what's interesting. By the way, I have to mention in terms of chemistry, one of the things that comes up is these kind of networks of sort of all possible applications of rules are also relevant to chemistry. If you imagine sort of a chemical reaction network, you can say these moves, which in this case are things about fundamental physics, but you can imagine this is some sort of named reaction in chemistry, and you say, what are all the possible named reactions that I can apply in this network of chemicals? And you can then ask the question, what can you get? And when you do chemical synthesis, you're typically doing something very much like mathematical theorem proving, where you're basically saying, what is the particular sequence of moves that I can make that get me from the initial chemicals to that particular chemical I'm trying to synthesize? And that's that's something that you can think about in the sort of theorem proving type way. And the thing I've been interested in very recently, last few weeks actually, is trying to understand kind of chemical computation in a way that's more general than that. Because in a sense, one thing you can do is say a computation is something where there's one input and one output. And that's kind of like what you do in synthetic chemistry, where it's like there's a bunch of inputs and then you're just going to get this one chemical out. But what if you allowed the possibility that actually there's this whole sort of, some piece of this whole branchial graph of possibilities that is the output of the computation? How can you think about doing computations in that kind of way? And what I realized is we have, if we think about computation at a molecular scale, we have one great example of where computation on a molecular scale works, which is biology. And so the question is, how can we use, can we think about things in terms of these multi-way graphs and all this kind of thing? Can we think about sort of computations where there isn't just one answer? Is there a way to think about that? And if we can figure out how that works, does that have implications for how we think about doing computations at a molecular scale chemically? And does that also have implications for our understanding of how biological systems work and thinking through sort of the logic of how biological systems work? anyway, always lots of things to say about this. Okay, we should probably go on to, that was an interesting question. Thank you. All right, lots of hands up. Who's next?
Let's ask Sahar.
Hello, I'm Sahar. I'm doing an MSc in theoretical physics in the field of cosmology. I wanted to ask, how did you doing a doctorate in high energy physics affect the rest later in your career, affect your later career?
To relate to things I've done subsequently in life, so to speak. I think the most, physics is a wonderful export field. People learn physics and then they go off and do interesting things in lots of other fields. I mean, one of the things that I like a lot about physics is it's kind of it's like use whatever methods you need, just get to the answer. That's a very useful kind of trait. And I know at our company, we hire a lot of people with physics backgrounds. I don't know whether we've crossed over now to having more people with computer science backgrounds than physics backgrounds. Computer science is slowly becoming more of an export field. Physics has been sort of the traditional export field. I mean, and also for me personally, I happened to manage to get through the education system pretty young. So, I got my PhD when I was 20 and things like that. And that was that sort of getting through the system early and having some early successes in a popular field was important for getting the confidence or arrogance or something to decide that I could actually work on sort of big, important problems. I mean, I think what actually happened, I worked on particle physics. I did pretty well on that. I got involved in sort of doing more serious computational things, built my first kind of computer language and when I was 20 years old, actually. That ended up turning into my first company. But the most important thing probably for me conceptually about building a computer language is in physics, it's like you have the world, you got to kind of break it down and see how it works. And the world already exists. When you build a computer language, you start from nothing and you just, you're creating everything. And to realize that one could do that and make something useful was really useful. And then to realize that the methodology of sort of creating something from nothing computationally, I was then able to sort of apply that in science. And that was kind of what got me started in sort of exploring the computational universe of possibilities, was because I kind of realized you could just sort of start from nothing and start inventing computational things and build something interesting from that. So I would say that the kind of meta methodology of physics of just figure things out by whatever means necessary, so to speak, is very useful. And sometimes I think, in terms of the detail, it's been very strange for me because I've been sort of out of physics for 40 years. And then have come back into it in a big way with our new physics project. And it's really weird. We just had a winter school for mostly physics graduate students who are interested in working on our project. And they were sort of telling me a bunch of things that they were doing about, QCD and things like that. And I felt like I had been, it was some kind of bizarre time warp, because it's like, I worked on that stuff in 1979. It sounds exactly the same today as it sounded like in 1979. But that's what happens in these fields where, the sort of the rapid growth methodologically kind of slowed down. And it is pretty much the same as it was 40 years ago. But it was strange for me to see. It's kind of fun for me because there are things that used to be called such and such, and now they've changed their name. They added a couple of extra authors to them, and they started to be called something different. But it's sort of been the same for a long time. But I think one of the things that for me is interesting. In fundamental physics, I think things have kind of slowed down a bit. Cosmology is an area where things are still hopping, but I'm kind of excited about the fact that our kind of physics project looks like it's injecting some new excitement and life into a bunch of fields that had figured out a bunch of interesting things, but were not really very well tethered to anything that could actually be applied in physics. Okay, we should go on here. Let's see, who's next?
Let's ask Shub.
Just wondering if you can hear me.
Yep.
Yes.
I can hear you.
Okay, awesome. Hi, Dr. Wolfram. Thank you for the fantastic eye-catching presentation. My name is Shub, and I'm a first-year biochemistry student at the University of Calgary. And so as you showed in your presentation, Wolfram Alpha is an extremely powerful, probably one of the most powerful scientific search engines out there. But although it is incredibly powerful and robust, it also has its limitations. For example, there have been times when I didn't get an accurate result when I entered a calculus limits inquiry, or
shocking.
Like, for example, in your presentation. So
okay.
is it possible, like, to troubleshoot these limitations and make Wolfram Alpha even more powerful?
So the first thing to realize is Wolfram Alpha is kind of a layer on top of Wolfram language. So if you really want to know what's going on, sort of, there's a cloud version of Wolfram language, and also most universities have site licenses for Mathematica and Wolfram language and so on. I mean, the thing to do is actually explore what's happening at the kind of Wolfram language level. I mean, the first issue for Wolfram Alpha is, can it do natural math understanding? Can it take whatever you type in and figure out what actual underlying symbolic expression that corresponds to? That can go wrong. That's sort of at some level not our fault, because it's trying to sort of pander to all the possible weird things people might type in. When it comes to actually doing the computation, well, then we are responsible for that. And I think the thing to understand, let's say with limits, is like start making plots of what the functions are doing. Start doing series expansions. And if you find one where you're really sure it's wrong, please send it in as a bug report, because that's how it gets better. But actually, in terms of limits, in the last probably 2 or 3 years, we've done a bunch of new work on limits. And I think you'll find, particularly in the context of asymptotic series. So you do power series expansions. You can also make asymptotic series. There's a whole sort of theory of asymptotic series, which hadn't really been developed that much, and we ended up having to do a bunch of basic mathematical work to sort of develop that theory to the point where we could use it. But I would try it in Mathematica, see what happens. If it doesn't work, please send in a bug report.
Okay, thank you.
Yeah.
Great. Let's go to an Israeli Schulich leader, Roni Hirshon.
Yep. Can you hear me?
Yes.
Yes.
Okay. Hi. First, Dr. Wolfram, thank you so much for the lecture. It was really exciting to hear about all these concepts. I did my bachelor's in computer science, and I'm doing my master's in computational neuroscience in Tel Aviv University. And I want to ask about the implications of your principles, especially computational irreducibility on free will and decision making. If you can expand on that.
Right. So I mean, what is free will about? There's sort of this mystery that we think that the laws of physics are at some level deterministic, yet it seems like we have sort of the free choice of what we're going to do. How can that possibly be consistent? Well, I think the thing to realize is, when you see a little critter that is, I don't know, some fly buzzing around that's near some light, and it just keeps on, bashing itself at the light over and over again, you say, that's not got free will. It's just, we can readily predict what it's going to do. It's just following some simple little sort of reflex that's making it do what it does. When we start talking about things seeming like they have free will, it kind of has a mind of its own, so to speak. That's when we can't readily predict what it's going to do. And this idea of computational irreducibility is kind of the idea that we'll never be able to predict what it's going to do, except by essentially following through each step. Now, one question is, what can we think has a mind based on this kind of idea? And the thing that is sort of a bit shocking is that this principle of computational equivalence says that lots of things have mind-like behavior. I mean, a common sort of statement is, the weather has a mind of its own. Well, does that really mean anything? Is that just some sort of weird animistic belief about the world? Well, actually, this principle of computational equivalence says, actually, all these fluid motions in the atmosphere and so on, they're doing a computation that's just as sophisticated as the computations going on in our brains. The only difference is that sort of the purposes that the weather is following are not aligned with any kind of human purposes. We don't have a language in which to kind of talk about the weather that makes it seem like it's doing human-like things. I mean, this comes up again when you think about extraterrestrial intelligence and kind of how do you tell whether this thing that's going on in the universe is a sign of intelligence. And what you kind of realize in the end is that there's this sort of space of possible computations and ways to represent those computations. And the question of whether, it's not really a question, is there extraterrestrial intelligence? It's more a question of how far away is it in kind of language space from us? How far, to what extent can we align kind of our sort of our way of thinking about things with what that system is doing? So I think in the case of, okay, so a thing that I've been thinking about recently, which I don't really have enough to say about because I haven't figured it out, and it's still a mess, is I had for a long time been very resistant. People would ask me about consciousness, and I would resist that vigorously. And I would say, you know, it's like defining, you know, when you define life, you can define life on Earth easily. It's sort of defined historically. But when you define, when you want to make a generalization of what is life, you end up finding there isn't really a generalization. It just becomes something which is computationally sophisticated. And I kind of thought the same was true in the end about consciousness, that it was, again, one of these things that we know what we have, but it's not generalizable. I've sort of realized very recently that I think I am beginning to understand that there is something a little bit different that can be said. It actually has to do with these kinds of non-deterministic many-answer computations that I was talking about before. One of the things that happens in quantum mechanics in our models is that basically the world is branching into all these different possibilities, but our brains are also branching into all these different possibilities. And the fact that we perceive definite things to be happening is a consequence of the kind of interplay between our brains branching and the actual universe branching. And this is a thing that's difficult to wrap one's brain around. At least I've found it that way. But I think that the sort of notion of consciousness ends up being something that I think we may actually get something, which is a not totally terrible definition of what's going on. And it has to do with the fact that there is a definite sort of thread of consciousness. There's a definite thread of thought happening that is different from this kind of highly parallel, lots of different things are going on situation, that it's something to do with the kind of the definiteness of our perception of what's happening. And so I'm really curious how that kind of plays out in the world of neuroscience. I was talking to a neurosurgeon friend of mine recently who was telling me with painful mechanism, in a painfully mechanistic way, what parts of the brain have to still be intact for one to have sort of the perception of consciousness in actual humans, so to speak. So I think that there's, in terms of computational irreducibility and neuroscience, one of the questions is there going to be a theory of neuroscience? Is it going to be plausible to have a narrative-like theory that can explain what's happening in brains? Or is one simply stuck saying, in the end, we're going to have a simulation of the brain, but we're going to be able to simulate it and say, yeah, we can make something that does like what the brain does, but we won't necessarily be able to break it down into pieces that kind of sound like a sort of a human understandable story about what brains are doing.
Amazing, thank you.
Yeah.
Let's jump back to a Canadian Schulich leader, Zach Fine.
Hi, Dr. Wolfram. Thank you so much for the talk. I'm Zach. I'm a first-year engineering science student at the University of Toronto. So you mentioned when math was invented, that obviously opened up a lot of new paths for research. And I'm wondering, as we get to understand and communicate with the computational universe more clearly, will there be room for research in the physical world anymore? And where might that be?
That's an interesting question. So the question of is it worth doing a physics experiment when you can just run a computer experiment instead? Well, the physical universe is, I think, effectively doing a computation too, but it's doing the most efficient computation that we can do in our universe. So in a sense, it would be a mistake to not use the most efficient computation that we have access to, namely the physical world, to figure things out, and to say only we have to simulate that. So I think we can. So one of the challenges of computers, for example, is to what extent can we get how close can we get to making use of all of physics in the things we build computers out of? So for example, in quantum computing, we have kind of the idea we're going to use quantum mechanics to do computing. I think that the details of how people imagine that's going to work is simply not going to work. I think when you think in quantum computing that you get all these sort of parallel threads of computation going on at the same time, what you forget in the standard formalism of quantum mechanics is that to get a definite answer, you have to kind of corral all these threads back together again. And that takes, it seems, as much or more effort as you gain by having all these different parallel threads. So there's this sort of question of, but the idea of quantum computing, one of the very powerful things that comes out of it is the notion of let's use more of physics than just the properties of metal oxide semiconductors to make computer-like things out of. And that's something that I think we can expect to continue to sort of leverage more of the physical world to do computations. But yes, I think, physical experiments, that's the best computer we have, we should use it. Sort of the making connections between one of the things we're really concerned with in our physics project is how do we go on the one side from the sort of computations, on the other side from the physical world, to sort of meet in the middle to see how we can actually find sort of experimental implications of the models we're looking at. I see a lot of hands up, and I unfortunately have a commitment that I have to go to in a few minutes here. So if we can, let's try and zip through. I'll do my best to zip through a few more questions here.
Thank you. Let's ask Yitzhak Weber in Israel.
Hi, thank you first of all for the talk. I'm a third-year student studying physics and electrical engineering in Bar Ilan in Israel. And my question is, when you talk about computational irreducibility, do you view it as inherent to math and nature as we see it, that they're simply patterns that we can't expect or we can't explain before they come to fruition? Or is it more that we simply lack the language with which to describe them? So they're too complex given our tools, but much like math stood in the mid-17th century where things were too complex before calculus gave us the tools to describe them, are we on the precipice of a similar advance in this field?
Right, subtle and interesting question. Okay, so the basic one feature of computational irreducibility is that whenever there is computational irreducibility, there are an infinite number of pockets of computational reducibility that also exist. So in other words, when to say, get me the whole answer and everything, that can be an irreducible thing. But whenever there is that kind of irreducibility, there will be places where you can kind of slide through and get to an answer. One of the things that's been most surprising to me about our physics project is I thought what was going to happen is that best case, we would find sort of a computationally irreducible description of the world. We'd be able to compute the first 10 to the minus 1,000 seconds of the evolution of the universe. We wouldn't be able to get any further. Turns out that there are some kind of ways of sliding forwards using sort of paths of computational reducibility. The two big paths that we've been able to use turn out to be precisely the two big pillars of 20th century physics, namely relativity and quantum mechanics, turn out to be two sort of pockets of computational reducibility in this kind of whole computationally irreducible general theory. Now, the question is, are there other pockets of computational reducibility that we might find? I think the answer is undoubtedly yes. However, the problem is that our descriptions of physics are ultimately based on kind of our sensory experiences and things like that. We have these notions of space and time and so on. And these are notions that ultimately derive in some sense from our biological evolution. And we might have the fact that we perceive space and time the way we do depends on the fact that our brain processing speed is slow compared to the speed of light, et cetera, et cetera, et cetera. We would perceive the universe very differently if that wasn't the case. Are there, alternative kinds of ways to think about the universe and therefore different pockets of computational reducibility? I think undoubtedly yes. It's kind of having seen what we've seen now, it's undoubtedly the case. Will we be able to relate those easily to what we humans know about? It might be very, very hard. It might be the case that those extraterrestrials that are really more like the weather than like our brains, they might perceive the universe using these different kind of pockets of computational reducibility, but it's really difficult to bridge that gap. And I think one of the things that we see, for example, in mathematics, is we see over the course of long periods of time, centuries, as mathematics develops, that we humans gradually understand more in some particular direction. That same kind of thing might happen. I don't think it will be I'll be very surprised if it's like, there may be a few specific little pockets of reducibility found, but I think in general, it's sort of a slow process. And unfortunately, I would really love to go on. These are terrific questions. The constraints in my life make me have to disappear here. But I just want to say one thing that people might be interested in. We do an annual summer school about science and technology and so on. People who are interested, please check it out. And also, if you're interested in, gosh, I mean, I end up doing a bunch of kind of live stream Q&A type sessions about, well, I'm doing one about our physics project actually on Tuesday of this next week. So if you have technical questions about the physics project, by all means, check that out. And I have to run. I'm really sorry. I would love to go on.
Thank you. Thank you so much, Dr. Wolfram, for your time to educate and inspire all of our Schulich leaders. We'll remember this experience for years to come. So we'll bid you adieu, and thank you again. If the Schulich leaders could just stay on for a couple minutes. I just